Professor Rebecca Nicholls has a master's degree from the University of Cambridge, where she studied natural sciences. And after a PhD in material sciences at the University of Oxford, she worked as a postdoc using electron microscopy to investigate a variety of materials from doped graphene to zirconia. Rebecca is now an associate professor and EPSRC research fellow in the Department of Materials at Oxford University. Her work focuses on structure and bondings of materials at the atomic scale, bridging the gap between experiment and theory. She is one of the authors of the OptaDOS code and now works on interpreting X-ray data as well as data from electrons. Rebecca's current research interests include predicting the vibrational spectra that can now be measured with the electron microscope and understanding defects in rare earth superconductors. So Rebecca, you can now put your presentation and the screen is yours.
Hopefully you can hear me, Paulina.
Yes, we can hear you. And so you can start your presentation.
And hopefully you can see my pointer moving as well.
Yes.
Brilliant. Excellent. Thank you for that introduction, Paulina. So I come under complementary field, and I'm going to be talking about electron microscopy and probing phonon vibrations inside the electron microscope. To start with, I'm going to tell you a little bit about my background in electron microscopy and the kind of science that I'm used to doing before moving on to this, for us, what's a relatively new field of phonon vibrations probed using spectroscopy in the electron microscope. So I am a material scientist, and as a material scientist, we have this kind of idealized view whereby the properties of a material are governed by the local structure and bonding, the way that atoms are stuck together. And if we were able to understand the relationship between the local structure and bonding and the macroscopic properties, we could modify the structure in some way as to optimize our material. So this is kind of completely idealized material science, and it applies to pretty much anything from batteries and materials for fusion in aerospace to kind of nanomaterials and catalysts. But actually, this is really not straightforward. And just the first part of it, understanding the local structure and bonding, is really difficult. And that's where a lot of my research is based, just understanding what the local structure and bonding in materials is. So as I said, my background is in electron microscopy. So this is a very idealized schematic of the electron microscope here. We have a sample, the beam goes through it, there are some lenses, and they normally form an image. But actually, those electrons that have gone through the sample carry information about the excitations that you can excite within the sample. So they've lost energy to the different excitations. And by dispersing it with a spectrometer, we can create along our CCD a spectrum, an electron energy loss or EEL spectrum. So this is what our electron microscopes look like. The sample goes in here. It's usually a 3 millimeter disc. Our electron gun is right at the top here. Electrons get fired down here, interact with the sample. Normally here we see perhaps an image, and then there is a spectrometer underneath here, and we get a spectrum at the end, or we use the cameras at the end and different kind of image configurations, lens configurations to get images as well. So we can use this in what's called transmission electron microscope mode. So we have a nice broad beam here, or we can do what's called scanning transmission electron microscope, where we focus this to a very small probe, and then we're able to move that probe across our sample. And at each point, we're able to take either diffraction patterns or images, or diffraction patterns or spectra, and create spatially resolved information about our sample. Okay, so what does our EEL spectrum look like? This is a very schematic drawing of an EEL spectrum. And generally, the largest feature in the spectrum is the zero loss peak, which is here. So this is all of the electrons that have gone through your sample and not lost any energy to it. So they haven't lost any energy at all. there's a broadening of this, which will be caused by the source broadening and other kind of instrumentation broadening. And that's generally used to tell us what the resolution of our spectrum is. So that's kind of relevant for stuff later on. Then we have the features moving on through our background here. So we have the plasmon region, this part here, which is collective excitations of the valence electrons. And then we have this decreasing background with the ionization edges on it. So our plasmon region is used to tell us information about the dielectric function. It can tell us things about thickness, and it can, in some circumstances as well, tell us a bit about bonding. Our ionization region, or also called single electron excitations, is where we excite electrons in the core to states above the Fermi energy, so the unoccupied states above the Fermi energy here. So this is very, very similar to X-ray absorption spectroscopy. And the intensity in our spectrum is governed by the unoccupied states we have up here. And so it's, to a first approximation, a way of probing our unoccupied density of states up here. So the nice thing, the same as with X-ray absorption, is that the energy that the edge appears at in the spectrum depends on the energy difference between here and here. So the energy difference between your core state and your Fermi state, your Fermi energy, and that is element dependent. So you have the information from different elements appearing at different points in your spectrum. So that can tell us about elemental composition, bonding and coordination, and valence, the valence state. So this part of the spectrum is actually used a lot to look at how the composition of your material varies spatially. For example, here we have some nanotubes. These are boron-doped nanotubes. And the idea with these is that you put the boron in to change the properties for gas sensing. And it was thought that the boron was included substitutionally within the graphene lattice. And what actually happens is you take individual nanotubes and put them inside the electron microscope and see how much boron is in them. So if you do a bulk measurement, you come up with such and such percentage of boron in your nanotubes. If you look at individual nanotubes one at a time, what you find is that 80% of them don't contain any boron at all. Of the other 20%, they're split into kind of two types of nanotube. One which look like this. When you do the elemental composition, so if we look at this elemental map here, this is a map where the carbon is represented in red, the boron is represented in cyan. And so where it looks white or pink, you've got a mixture of carbon and boron. So you can see that all of the boron is contained within the core of the nanotube. And you've basically got disordered graphitic layers around the outside of the nanotube. So this is how most of the boron goes into the nanotubes. The third type of nanotube is similar to this, but it doesn't have this kind of protective layer. And what you see is that you get boron oxide forming along the edges here. So it kind of shows the power, really, of being able to do the spatial chemical analysis compared to the sort of bulk analysis, where you get a kind of average of how much boron is in all of the nanotubes. When you start doing the individual nanotube analysis, you find that most of them don't contain boron. The ones that do contain boron don't contain it, so that you have boron atoms at the surface, which was what was expected, and kind of the gas sensing results were interpreted in that way. So a lot of the EELS measurements get used for this kind of thing. So using the spectra to map where the elements are present in the material. The other thing that I kind of quickly wanted to mention is that although there's a lot of similarities between the X-ray absorption and the electron energy loss spectroscopy, the range of edges that we can see is much, much smaller, because our spectrometers go up to about 3000 EV. So we can only see edges within that energy range. So for example, a copper K edge at around 9000 EV, we'd never be able to see. So this is a periodic table color coded according to which edges we can see in the spectrometer in EELS. So the green elements are the ones where we can see the K edges. So you can see that we can only see the K edges of a relatively small number of elements. The blue ones are the L23 edges, and then the pink ones here is mainly M45 edges. that we see in the microscope. So some of these edges potentially give us a lot less information about the type of bonding that's going on, but they can be used for the elemental mapping. Okay, so interpreting the spectra. So with all spectra, you get a lot of bumps and wiggles, and actually interpreting that in terms of the atomic structure can be very difficult, especially if you're looking at something that is either an interface phase or a nanomaterial. So you haven't necessarily got a bulk that's relevant to use for fingerprinting. So it's the cases where you don't know what your structure is, or you've got some kind of defect that you're wanting to understand. In those cases, it's difficult to fingerprint, and actually using simulated spectra can be really, really important. So the main aim here is not to just reproduce the experimental data using simulation, but to actually really understand what the problem is. And it's really important to keep that at the center of planning the modeling. Okay, so how do we go about modeling EEL spectra? So we start with the double differential cross-section, and anybody who's interested in this kind of thing, this is a really, really lovely paper down here, which talks about the double differential cross-section and the similarities between electrons, neutrons, and X-rays. So this is just very, very general. What we're interested in is the number of particles that have been scattered divided by the number of incoming particles. So how much of our beam is scattered? Putting that a bit more accurately, the number of particles scattered per second into a particular solid angle in a particular direction and with a particular range of energies, divided by the number of incoming particles per second per centimeter squared along the Z direction with certain momentum and energy. So this here is a totally general equation, word equation. I'm not sure it quite merits equation. Here is it in a more equation form. So this is still totally general. And these things highlighted here are the things that we need to specify specifically if you're looking at electrons, neutrons, or X-rays. So your Hamiltonian changes, your beam current changes, and the relationship between K and E is different. So if I do that for electrons, I get something that looks like this. This one here is for electrons. This is just for kind of core loss edges. This one here is for X-rays. So you can just see, without worrying particularly about the details of this, how similar the two techniques are. So this would be, say, comparing X-ray absorption and electron energy loss spectroscopy core loss edges. So in general, the way that we go about modeling core loss edges is by using some kind of plane wave band structure DFT code to calculate the core and valence wave functions. So those are these here. So you start off with a core state and you go to a valence state. So you need these wave functions, and then you need this matrix element here. So generally we do that using a DFT code, and then use something like Optidos, which reads in these matrix elements, forms a spectrum, and then adds things like instrumentation and lifetime broadening. So I wanted to give you an example of the kind of work that we do using this approach. And this is a zirconia interface layer. So zirconia is used for reactors. It's used for fuel cladding and components. And unfortunately, it oxidizes. So the metal oxidizes to become ZrO2. And this process, you get a growth of the oxide, it stops, you get another growth of the oxide, it stops, and it grows again. And at some point, you get catastrophic failure. And that is very bad. And so what happens is that these materials are taken out of service very early in their lifetime. And there's lots of work being done to try and understand this oxidation process. One thing that was found, this is work by Nani, this was her PhD work at Oxford, that there was a suboxide phase, a phase with ZrO, which was forming at the interface between the oxide and the metal, and it was thought to play some sort of role in kind of controlling this oxidation process. So understanding the structure of this was very important. Unfortunately, the region of the interface phase is very small. And so this is the kind of diffraction pattern that you get from it, which isn't really great. But if you do EELs across here, so this is low loss EELs. So this is collective excitations of the plasmons here, which is collective excitation of the valence electrons. And what you can see is you've got very distinct signatures from the metal, from the oxide, and from the suboxide. So the suboxide is not a linear combination of the metal and the oxide, it's some other specific phase that's forming here. And so Sergio Lozano Perez, who was Nani's supervisor, came to me and said, we've got this interface phase, we've got the EEL spectra for it, can you model it? And I said, we can have a go. What is the structure? And he said, we don't know. And actually, that then makes it a very interesting question, because the first thing that you do when you're kind of modeling pretty much anything with DFT is you put a structure in. So what do you do when you don't know what the structure is? Well, the first thing we did was look in literature. And in the literature, in the big crystallographic textbooks, there's a ZRO cubic structure. But the other thing we did was ab initio random structure searching. And this sort of being able to predict crystal structures using just first principles is something that's only really happened within the last kind of 10, 15 years. So this is relatively new. And there are several different ways that you can go about doing it. We use specifically the ab initio random structure searching algorithms developed by Richard Needs and Chris Pickard at Cambridge. It's known as AIRS, and it basically, you kind of randomly pick a box, randomly generate a box and randomly put atoms in it. We know that we've got ZRO, so we put in equal numbers of ZR and O. You then minimize the forces to the local minima, and then you rank them all according to energy and hope that you've done it enough times that you found the global minima. So that's what's done here. Here you can see we've got the ZRO, and each one of these dots corresponds to a separate calculation. So there are kind of thousands that have gone into producing this here. And you can see that we have a point here on the convex hull. So we have a phase down here, which we'd expect to be stable. And in fact, we don't have one phase, we have two phases. So there are two phases here, an orthorhombic and a hexagonal ZRO structure, which are indistinguishable using DFT. One thing you'll notice is that neither of these are cubic. So the cubic phase is way up here in terms of energy. So we don't expect this one to be stable. And there's quite a lot of work, theoretical work being done on this in terms of how it has negative phonon modes and you'd expect it to transform into other materials. So this isn't thought to be stable. If you go back to the crystallographic textbooks and where it originally came from, it's a paper from 1952, I think it is. And it's a footnote where they just say, I've made this as well, and the lattice parameters, and then it gives a huge range of lattice parameters. So it's kind of gone from there into the big crystallographic textbooks, and then from there into the kind of scientific memory for this field. So we're choosing all three of these structures to investigate. And what we do is we use them to generate diffraction data to compare to the diffraction patterns, and to generate EEL spectra to compare to the EELS data. And so what you can see is that the cubic and the hexagonal structures are able to interpret the diffraction patterns, and the EEL spectra you can interpret using the orthorhombic and hexagonal structures, but it's only the hexagonal structure which you can use to generate diffraction and EELS data that fit with the experimental data. So we believe that this is the structure that's forming, and we think that it's the hexagonal structure that's forming rather than the orthorhombic structure, because the original metal which is being oxidized is hexagonal. So we think that the symmetry of the metal is controlling the symmetry of the suboxide that's forming. Okay, and what's quite nice now is that this crystal structure has been put into the EBSD databases. These are EBSD maps, and originally so we have the metal down here, the oxide up here, and originally they'd just be black along here where there was a phase that wasn't fitted, and now you can see that it's all nice and yellow all the way along here. So the reason I particularly like this story, is because it needed the combination of experiment and theory to be able to solve the structure. The theory alone predicts two structures that it can't distinguish between, and just with the experimental data, we're not able to interpret what the structure is. So we need the combination of both the theory and the experiment to be able to kind of solve the structure. So that kind of gives you kind of an idea of my background and the angle with which we're moving into the phonon spectroscopy. which is what I want to talk about next. So Anders has already given us a lovely introduction into phonons and what they are, the vibration modes. So the phonon modes being the vibrational modes from a quantum mechanics point of view, the collective wave associated with a specific wave vector, and the fact that we get these phonon dispersions, which are usually probed with inelastic neutron or inelastic X-ray scattering. And the reason that we're interested in these is that they're central to a whole variety of theories, from structural phase transitions to the stability of polymorphs. So there's lots of reasons why we want to know about the phonons in materials. So why are we interested in phonon eels now? So the phonons in the electron microscope have been seen for a long time in terms of like the diffraction patterns and the thermal diffuse scattering. But for a long time in eels, they have just contributed to a broadening of the zero loss peak. So we haven't actually been able to see the phonon vibrations themselves. In about 2014, there was a development in hardware by Neon and Andrei Krevenek. And what you can see here is 2 zero loss peaks. So it goes back to the resolution that I was talking about before, and how we use the full width half maxima of the zero loss peak to measure the resolution of our spectrum. This is what was state of the art before about 2014, 2015. So it used to be about 0.2 millielectron volts. That was considered state of the art. With the developments in hardware, this is then considered state of the art. So we've moved from 200 millielectron volts down to about 16 millielectron volts. So this was the initial kind of huge jump in the hardware. And there's been continuous improvement since. And I think that the best data now is around 6 millielectron volts. So this is huge for us. We have had to change our units. We used to think of our resolution in terms of EV, and now we're having to think of it in terms of MEV. We're getting more information across the whole spectrum, but what it really means is that for the first time, we're able to see phonons in our eel spectrum. So this is really very exciting. What are the advantages of it? So why not just do IR or Raman? Because these are kind of fairly straightforward, and there's one in most labs. But you only look at the gamma point. You don't look at the whole phonon dispersion. Again, you could do inelastic X-ray scattering or an inelastic neutron scattering. So why use the electron microscope? And I think that really it's a complementary technique. In eels, we probe volumes which are 20 orders of magnitude smaller than in the neutron X-ray techniques. So we're looking on a different kind of spatial scale. We can probe higher energies because our spectrum just kind of keeps on going. So hydrogen modes are very easy for us to look at. We also can do the chemical analysis in the same instrument as well, because we've got the rest of the spectrum as well. So we can combine it with the chemical analysis very straightforwardly. So the new generation of microscopes in the UK, we were very lucky because the third of this new generation of microscopes was delivered to our national facility up at SuperSTEM. And the first kind of level of excitement was, can we see a phonon? Yes. And then this is the kind of level of experiment we were doing at the time. Can we distinguish between cubic boron nitride and hexagonal boron nitride? And so here we have the spectrum here from cubic boron nitride. Here we have the spectrum from hexagonal boron nitride. And you can see that our phonons are at different energies, which is what you'd expect because we've got different polymorphs of the same material. So yes, we've got a different phonon signal between the two of them. So this was very exciting at the time. And then with my collaborators at SuperSTEM, they went on to start probing momentum resolved eel spectra. So this originally was done by tilting the beam. So by tilting the beam, you can change where in reciprocal space you are collecting your eel signal from. And so you're able to collect momentum resolved phonon spectra. So these are the first momentum resolved phonon spectra collected inside the electron microscope. They are not the nicest of data, shall we say, and if you're used to looking at X-ray data, then they're not super impressive. But these were very exciting for us because this was the first time it was done. And also it was kind of pushing the machine into a direction it wasn't supposed to go. So it wasn't very optimized. But you can see we've got a different number of modes, things are changing. And now we want to actually be able to interpret what's going on. So we want to know which modes are contributing, and we want to be able to model the experimental data. So the next question is, how do we go about modeling this data? So the phonon vibrations that we're looking at are just the materials and sample properties. So the phonon vibrations we're seeing are no different from the phonon vibrations that anybody else sees. And we can actually follow an approach which is fairly similar to the neutron and X-ray scattering communities. And really the difference is coming from the type of particle being scattered and the type of interaction between the particle and the sample. So I can go back to my double differential cross-section because this doesn't care what the scattering event is. It doesn't care what the particle is, it doesn't care what the scattering event is. So this is where I start again. And again, my equation is looking like this, and these are still the only parts of it that I need to change. If I go through and put in the Coulomb interaction and use the correct way of converting between K and E and put in my beam current, I get something that looks like this. Don't need to worry too much about the details, but I just want to point out that this thing here can be rewritten as this, which is a correlation function. So this is kind of similar to X-rays again, but this here is a total density correlation function rather than an electron density correlation function, which is what you would be using in X-rays. So here we're looking at the total density. So we've got the nuclear density as well as the electron density. And if I put that in, I get an equation that looks like this. And the bits that I actually need to calculate are here. This thing here, I've got 1 over q to the 4 and this thing here. So this is what I'm calculating. So what are all these things? Well, here we have an atomic form factor, which is tabulated. This thing here is just atomic number. This thing here is a Mulliken charge. We've got Debye-Waller factors. We've got phonon eigenvectors. We've got atomic masses. We've got atomic positions, and we've got phonon frequencies. The nice things about these is that they're all either known or I can calculate them using DFT from first principles. So now I've got, as far as a formula, a way of predicting my phonon EEL spectra, I can go away and do a DFT calculation, calculate or look things up which are tabulated, and then plug things in and predict the spectra. Okay, so we had to go. So this is our cubic boron nitride. This is going from the gamma to the X position in reciprocal space. And here is the prediction in blue, just using the DFT calculation and plugging it into the equation that we've come up with. And actually, the match is pretty good. So that was very exciting. And we can also do things like look at it in reciprocal space. So you can see here that we've taken the band structure in reciprocal space and color coded it according to which modes are contributing and how much they're contributing. And so what you can see is that we have some modes that don't contribute at all, and then some that do. And we have an acoustic mode coming in here, which is this thing coming in here. And we can do that. So this is going a different direction through reciprocal space, and the agreement, again, not too bad. So what this has done here is taken the band structure for the cubic boron nitride going from the gamma to the X points, and I've color coded it according to what you would see with X-rays, neutrons, or electrons. So one thing that you can see is that here for electrons, we get really high signal close to the gamma point, which doesn't happen for either neutrons or X-rays. So we're kind of getting complementary data using the different techniques. Okay, so the spectra can be calculated from first principle and matches relatively well to the momentum resolved initial experimental data. it allows us to really interpret our experimental data in terms of the specific modes that we're looking at. And it also importantly allows a prediction of spectra. So this work has been used now in a variety of things. It's used, so since we did the initial momentum resolved experiments, there's been some much more careful planned experiments on things like graphene, hexagonal boron nitride, with this lovely work in this paper here, where the spectra, to be honest, look much nicer than our initial data, but they match really well using the similar theory there. And also they've been used on things like silicon germanium quantum dots in this work here. One thing that I just want to point out, and I don't have a slide on it, but I meant to mention, interesting things I know from talking to Paulina about this kind of way of approaching things at the moment. So we've used the atomic form factors, and then we've used the charge minus a Mulliken charge, so a way of scaling it. This obviously is a huge simplification and not necessarily the best way of doing this, because our initial data was not super well resolved. It didn't really matter for the kind of initial experiments that we were doing, but the treatment of this, I think, will matter more going forwards. So head back. But the last thing I want to do then is acknowledge all of these different people, particularly Quentin, Frederick and Demi at SuperSTEM for the wonderful work on the Phonon experiments, which is really, I think, which is really very exciting. And thank my group and thank you for listening and for inviting me to come and talk to you.
Thank you very much, Rebecca, for this really excellent lecture, which is now open for comments and questions. And you were referring to this to the scattering factors. What can you predict what would happen if you apply aspherical scattering factors? Because I assume you were using spherical ones.
Yes, so at the moment we're using spherical scattering factors here, and at the moment we're just scaling them according to how much the Mulliken charge is. The Mulliken charge comes out of the DFT code, and we're basically just kind of drawing a sphere around an atom and summing up the charge within it. So we've tried using Hirschfeld charges as well, and it didn't make a huge amount of difference, kind of the way that we divided it up. But I mean, one thing that I think it definitely being able to do something nicer and more careful with this, I think, is an important way of kind of taking it forwards in terms of better experimental data is now being produced. So we need to be kind of more careful about how we treat that.
Okay. And we have two questions from Daniel Ugarte. The first one concerning the identification of hexagonal zirconium hexagonal phase is a very anisotropic structure. Have you explored anisotropy to make your ELS spectrum understanding more precise?
So we did at the time a look at the orientation dependence of the spectra. And off the top of my head, I can't remember how much the variation was, I'm afraid. I think, so trying to understand the orientation relationship between the suboxide and the metal is something that people were very interested in, because that kind of controls the diffusion properties of the material. And I think there was some work done on EBSD to try and get the orientation of the metal and the oxide, and then look at the orientation of the sort of the suboxide in between. But I think there was nothing very concrete came of it, I'm afraid.
Mm-hmm. And the second one, you emphasized the high spatial resolution and momentum mapping capabilities of Phonon's studies using a different momentum transfer. What about the strength of normal Raman using resonant excitation as exploited to study single carbon nanotubes in 1 micron laser spot? Can you comment about the relevance of selection rules in energy and momentum between both techniques for further progress?
Yes, so I think definitely there's lots of complementarity between different techniques. So something like the nanotubes are potentially one thing that can be studied with Raman, with better spatial resolution. But some of the things that people are looking at with the ILS spectra at the moment are interfaces, because that gives you spatial resolution of the phonons across an interface, which has made people start to have to think about what that means, because obviously phonons are generally thought of in terms of the collective vibration. So what happens when you localize the vibration? And I think something like that would perhaps be much harder to do using Raman, because the kind of laser spot would be too big for that. So I think that there's different things are probably better for slightly different samples. In terms of the kind of core loss stuff, the energy and momentum, so differences between both techniques. So the momentum resolution at the moment is not necessarily that good in eels. So definitely the first experiments we did, our momentum resolution wasn't very good at all. And I think that we couldn't even tell exactly what it was, because our prediction of what it should be would mean that our spectra were even worse than they were. But I think that has got better. People have got a better idea of what they're looking at. And also the spectrometers have been replaced. So they've been kind of designed to better do these types of measurements. In terms of the core loss stuff, how you set up your EELS experiment can make a big difference on whether you're looking at Q goes to 0 or looking at kind of larger Q scattering. And then depending on which you're doing, you get kind of more dipole-like or less. And so that does affect the selection rules. So in some sense, understanding the experimental setup and controlling the experimental setup for eels helps you be able to define and control your energy and momentum. That's kind of lots of bits of stuff together, but hopefully that answers most of that question.
Thank you. And there is a question from Anders. Anders, could you ask it yourself?
Yes, so thank you very much for a very interesting talk. So my question, of course, has something to do with molecules. Can you do molecular systems, or will there be too much beam damage or other effects limiting you? And what temperatures are possible to do?
So those are both really very good questions. One thing that we can do in the electron microscope is collect a spectrum when we have our beam next to our material rather than going through our material, which can then greatly reduce our beam damage. So we have started trying to work on molecular systems, but doing it by putting our beam next to our sample rather than on our sample to be able to reduce our beam damage. The trouble with that is that then our theory doesn't quite hold anymore. And that's, I think, because of the way that we're considering the charge transfer. And so we're working on a modification of this where we go right back to the beginning and change the way that we're dividing up the charges and then getting a different equation. But that is a really interesting question, and it's not necessarily an easy extension, but it's definitely something that's interesting and definitely something that we're working on. And then what temperatures are possible? And this also is a very interesting question, because there's always the question of what the temperature is inside the electron microscope when you're hitting it with a beam, although hopefully if you've got your beam next to it, it potentially has less effect. So it is possible to control the temperature inside an electron microscope, and there's lots of kind of heating holders and stuff. But the type of microscope that has the monochromators on in the new hardware originally isn't designed to have the heating holders in it. I think that the manufacturers are working on being able to combine all of the different capabilities together. But yeah, because that would be good.
Yeah, so a follow-up question or a comment. I think what I have seen now using a bit of electron diffraction is that especially solvates and hydrates are not very stable in the electron beam, and probably that goes in general for molecular crystals. So being able to cool it down would definitely do good, but of course you also need to have some phonons available still, so you shouldn't cool too much, I suppose.
Yeah, I think we'd be unlikely to cool too much.
No, okay.
But yeah, that's definitely interesting.
Yeah. Next question comes from Hansbert Birgi. Which fraction of the brilliant zone can you access with your instrument?
So we can access the whole of the brilliant zone just by tilting. So I think perhaps for some X-ray measurements, they tend to go further out because near the center of the brilliant zone that the signal isn't very high, but we don't suffer from that problem. We have good signal very close to the center of our brilliant zone.
Okay. Leonard Correa, are experimental conditions such as noise, energy, resolution, etc., included into simulations before comparison with data? A prior Debye-Waller factor utilized in the simulations or some kind of data feed is performed?
So some yeses and some nos there. So noise isn't included, but energy resolution is included in the simulations. And actually the Debye-Waller factors that we've used are ones that we calculated from DFT. So the same calculation that we got our Phonon eigenvectors and everything else from, we also used to calculate the Debye-Waller factors.
Mm-hmm. Daniel Ugarte, thanks for the nice presentation. When you position a focused electron beam close but outside to molecules or surface, do you enter a non-linear polarization regime?
I think that we don't know at the moment. So at the moment, we're doing the kind of experiments where you start off quite far from your material and you go towards it and you look at how the phonon spectra changes. And I think that we don't quite understand what's going on at the moment. And I think also that you have to go further away from the material than we had originally thought to get no phonon spectra at all. So when we thought originally we would be in a kind of no spectra, like not far enough away to, not close enough to be able to excite the phonons, we're still exciting them. So I think that what we call aloof mode, which is where you're outside your sample, it's still quite a lot of work to be done.
Mm. Okay. Then is this an effect of delocalization?
Quite possibly. I guess it's an effect of the field created by our beam being quite long range, and we're expecting it to be kind of dipoly at that point. But I think that there are possibly delocalization, but there are effects that we don't totally understand going on at the moment.
Mm-hmm. Yes, Paulina, do you have any question?
So do you need to somehow build your own microscope or trick what is available on the market, or how easy is to have such setup in your lab to do this kind of measurements?
So it's not easy. So Neon, the kind of microscope manufacturer who have kind of led the way with this, but I think that Neon are a very approachable company. So if you had something specific that you wanted to be able to do, then you would kind of take your wish list to them and find out how much it was going to cost. Then start writing grants, I guess.
Okay. As I do not see more questions nor comments, let us thank both Anders and Rebecca for their really excellent lectures. Bravo.